For decades, automotive engineering treated vehicles as closed, deterministic machines. But the transition to Level 4 and 5 autonomous architectures forces these systems out of controlled environments, turning them into complex cyber-physical networks. This shift exposes the vehicle to multiple, distinct dimensions of risk. Traditionally, engineers focus on two main areas: random physical hardware faults, managed by ISO26262, and intentional malicious cyber attacks, governed by ISO21434. But full autonomy introduces two additional threat models. We have to account for environmental edge cases and sensor limitations, addressed by SOTIF or ISO21448. And because vehicles now rely heavily on neural networks, we must manage the statistical uncertainty of AI models, defined by ISO8800. The default engineering reflex is to take these four radically different risk profiles and compress them into a single quantitative metric, such as a master fit rate or a system-wide probability score. This creates a significant mathematical challenge. Random wear and tear and intentional adversarial logic follow entirely different probability distributions, making them difficult to reconcile within a single scalar value. To understand how these models interact, consider the MCU Watchdog timer. This is the hardware safety mechanism designed to detect if a microcontroller gets stuck in an infinite loop. This spreadsheet shows a standard FMEDA analysis. The Watchdog timer row is granted a 99% nominal diagnostic coverage, satisfying strict safety targets. The residual fault rate equals the total baseline fault rate multiplied by 1 minus that 99% coverage metric. But this deterministic model changes when we introduce a threat analysis and risk assessment. Suppose an external attacker successfully gains access to the vehicle's wireless interface and breaches the internal CAN bus network. The adversary doesn't need to break the physical silicon. They simply forge a clear register command over the network and send it to the controller, forcing the hardware watchdog to disable itself. The physical circuitry remains perfectly intact, yet software manipulation has effectively erased its protective function. To model the actual risk, we expand the formula to calculate effective diagnostic coverage, factoring in the probability of a successful cyber attack. If significant, the effective coverage vanishes. A system architecture can carry perfect ASIL-D certification on paper, but it is rendered unsafe at runtime if the probability of a network attack is ignored in the baseline equation. The standard architectural countermeasure against CAN bus injection is the implementation of AUTOSAR secure onboard communication protocols, utilizing AES-128 cryptography. These protocols attach a message authentication code, or MAC signature, to active control messages. This requires the system to mathematically verify the integrity of every signal traversing the vehicle network. However, this security layer collides with the absolute physical constraint of functional safety, the Fault Tolerant Time Interval. Cryptographic verification demands significant computational cycles. Generating and verifying those MAC signatures forces the microcontrollers to expend time, creating inherent processing delay. This timeline represents a strict 50-millisecond window for a steering actuator. The fault-tolerant time interval is the absolute maximum time allowed to detect a failure and transition the physical system to a safe state. When we inject that cryptographic latency into the control loop, it stretches the sequence. The combined processing time forces the response past the 50-millisecond deadline. The system fails the safety goal at the exact moment the sum of these times exceeds the allowed interval. In the effort to secure the network from remote intruders, the system effectively introduces the very timing failures it was designed to prevent. This friction between logic and physics is even more severe inside the vehicle's decision center, the neural processing unit executing deep learning models. Inside the NPU memory array, cosmic rays cause bit flips within the SRAM storing neural weights. However, because neural networks use a highly distributed architecture, simulations reveal a masking effect. Localized physical faults are absorbed by the network's tolerance, leaving the final algorithmic output perfectly stable. The true systemic risk lies in the epistemic uncertainty of the AI model itself, specifically when it encounters a shift in its training data distribution. A large metal truck in an intersection generates severe multipath radar reflections. The hardware functions perfectly, but this environmental data overwhelms the model's predictive capability. This requires an uncertainty wrapper in the software architecture. This wrapper monitors the confidence indicator, watching for statistical deviations. For AI-driven perception, trapping the algorithm's statistical hallucinations is more critical to passenger safety than counting physical transistor failure rates. Resolving these conflicts requires moving past software-only patches and adopting a physically asymmetric hardware architecture. We address the cryptographic latency paradox by offloading AES computation to dedicated hardware security modules and utilizing event-based network architectures. In hypercritical chassis control loops, we truncate the MAC signatures. This deliberate engineering trade-off prioritizes the physical fault-tolerant time interval over maximum network security. The ultimate failsafe must account for both AI hallucination and total system compromise. This diagram shows a massive system-on-chip paired with a physically separate microcontroller. Zooming in, the bus isolation IC creates a hard hardware barrier, severing external network access. We call this isolated environment the safety island. The safety island acts as the final judge. If the AI uncertainty wrapper spikes, or a ransomware attack compromises the main operating system, the safety island physically severs power to the corrupted chip. Once isolated, the vehicle ignores all external input. The safety island relies on its own deterministic code to execute a minimal risk maneuver, bringing the vehicle to a controlled stop. The path to viable L4 autonomy is found in these hardware boundaries, where conflicting safety standards are integrated into a single, resilient system-theoretic architecture.